Hello everybody and welcome back. We're going to continue looking at the 2011 senior paper. We're on to question number 2 in B part. That's the written part, so we need to look at full solutions. So how about we take a look at question number 2. It looks like it's going to have 3 parts. So, A part. First, determine two positive integers x and y with 2x plus 11y over 3x plus 4y equals 1. So I notice we have an A part and we have a whole bunch of preamble before B and C. So I'm guessing that the way this is structured, A is going to be very important motivation for what's going to come in the middle. I could read what's in the middle, and it's usually a good idea to actually read the whole question, but I like to do these videos piece by piece, so we're just going to do A part right now. So we got ourselves a scrap piece of paper here. So we want 2x plus 11y over 3x plus 4y equals 1. So we have two unknowns, x and y, and these are going to have to be positive integers. And we're just going to have one equation. What we're going to do is we're going to multiply through the denominator and just get an equation in x and y. So this isn't going to solve solving for exact values of x and y. You can't have one equation and two unknowns and be able to solve for those unknowns. So what we're going to have is we're just going to get a relationship between x and y. So 2x plus 11y equals 3x plus 4y. What we want to do is we want to bring all the x's to one side and all the y's to the other side. So let's bring all the y's over to the left-hand side. That simplifies to 7y equals x. So once we pick a value for y, we multiply it by 7, we get our value for x. So we could take y is 2 and we'd get x is 7. Or we could take y is 1 and x is 7, y is 2 and x is 14, or y is 3 and x becomes 21. Any of these values will work because it satisfies the relationship and so then satisfies the actual equation here. So once we specify y, we multiply it by 7. We get x is equal to 7 in this case. We could have tried any other value for y. We want to specify the y value rather than starting with the x value and figuring out the y value because y has to be a positive integer. And so if we pick x as 13 or x is 1 or something, we're not going to be guaranteed that y will be a positive integer. So we start with y, and then we multiply it by 7 to get x. So x and y equals to 7 and 1. Will satisfy the equation. But need any other pair so that x is 7 times y will work. Okay. So now with A part done, this should motivate our well, not a preamble, I guess it's a mid-amble. Now, let x and y be two positive rational numbers with let u and v be two positive rational numbers with u less than v. If we write u and v as fractions, u equals a over b and v equals c over d, not necessarily in lowest terms. Okay, so we could have 2 over 4 if u was a half. We could definitely have that. So not necessarily in lowest terms, and with a, b, c, and d positive integers. Okay? And then the fraction a plus c, b plus d is called a mediant of u and v. Since u and v can be written in many different forms, there are many different mediants. Okay? So a mediant is sort of like if you didn't really know anything about fractions and you thought, oh, how do you add these fractions? You would add the tops and add the bottoms. Which we know is not actually how you're supposed to add fractions. You're supposed to find a common denominator. But a mediant is sort of like very naively adding fractions. Okay. In A, we showed that 1 is a mediant of 2/3 and 11/4 because we found that 14 over 21 plus 11 over 4, the mediant there is 1. So we definitely wrote u in a different form, 14 over 21. We can also see that 2 is a mediant of 2/3 and 11/4 because we can write 2/3 as 6/9 and 11/4 as 44/16. 6 plus 44, we add the numerators, we have 50 over 9 plus 16. Add the denominators together, that's 25. 50 over 25 is 2. Okay, so we have a new concept of mediant, and we've seen it already in part A. So this sort of equation would show us, if we put our desired mediant over here, we can set up this sort of an equation and solve for x and y. B, prove that the average of u and v, namely 1/2 u plus v, is a mediant of u and v. Okay. Well, first, let's figure out exactly what this guy looks like. If we keep our fractions a over b and c over d, again, not necessarily in lowest terms, we can figure out exactly how to write the average. It's 1/2 u plus v, that's 1/2 a over b plus c over d. So we need to find a common denominator. Well, the easiest way to do that is just take the one denominator, multiply top and bottom of the other fraction by it, so AD over BD. And the first denominator, we multiply top and bottom of the second fraction by that. Right, now we have a common denominator of BD on the bottom. So 1/2 AD plus, we'll rearrange things so that it's in alphabetical order. BD, and then multiplying through by 1/2, we multiply the numerators and multiply the denominators. So we're left with AD plus BC over 2BD. And we want to show that this is equal to a mediant. Okay? So if we're going to be a median, well, we use sort of the equation we had before, but instead of 2/3 and 11/4, we use A, B, and C, D. Okay. So AX plus CY over BX plus DY equals AD plus BC over 2BD. Okay. Well, if we want to solve this, again, we're going to be looking for a relationship in X and Y most likely. But the best thing to do would probably be to start manipulating. So 2BD AX plus CY is going to be AD plus BC BX plus DY. Okay. So expanding out the left-hand side, we get 2AB dx plus 2BC dy equals AB dx plus AD squared y plus B squared CX plus BC dy. Okay. Well, looky here. I have a 2AB dx, and I have an AB dx, and I have a 2BC dy and a BC dy. So I can cancel these out. Okay. Once again, just like we did in the first case, we want to rearrange and collect like terms. So we'll bring all the x's onto one side. AB dx minus b squared cx. And AD squared y minus BC dy. We can take out a common factor of b here. B and AD minus BC x. And we can take out a common factor of d here. AD minus BC y. Okay. Now, in order for these to be equal, let's see here. I'd like to divide by AD minus BC. Can I? Is that going to be 0? That's a good question. Is that going to be 0? I don't think it should be 0. Okay, if AD minus BC equals 0, then AD is equal to BC. And AD over BD is equal to BC over BD. So AB is equal to CD, or rather U equals V. But we know that U is less than V. So by contradiction, AB or AD minus BC is not going to be equal to 0. That means we can divide by it. So we have bx equals dy. So that's the relationship we need to satisfy in order to show that the average is a median. Okay? Right, we couldn't just, by the way, we couldn't just divide through AD minus BC at this step because there's no way to know that it couldn't be 0. We had to show why we can divide through by AD minus BC. We need to show why it's not 0. We have a lot of positive integers floating around, but we have a difference in positive integers here, so we could very well have a 0. But we showed that that would imply U equals V, but we know U is less than V, so we don't have any problem there. So now we need to find x and y so that bx equals dy. And the quickest way to do something like that is to just take x to be whatever we need to multiply y by, and y to be whatever we need to multiply x by. So x to be d and y to be b. So this can be satisfied with x equals d, y equals b. Right? BD is equal to DB. Because we've satisfied that relationship, and that's the relationship we needed to satisfy in order to show the average was a median, we know the average is indeed a median. of u and v. Okay. So we explained what we were doing at each step. In particular, we showed why we can divide by 0. That was quite important. I imagine there was a mark lost if you didn't do something like that. And we showed that the average is a median. All right, C, the last part. Prove that every median m of u and v satisfies u less than m less than v. Okay, these are strict less thans. Okay. Well, let's see. I know the general form of a median. And so it's ax plus cy over bx plus dy. So I know what that looks like. So I know what m as a fraction will look like. How do I show that it's greater than something? Well, we'd have to show that there's a positive difference, so that m minus u is definitely greater than 0. So we need to show that m is greater than u, but also m is less than v. If we subtract u from both sides, we show that m minus u is positive, and subtract m from both sides, v minus m is positive. So that's what we're going to try and do. Okay, we know a, b, c, and d are positive integers, and we know that c and x and y are positive integers. Okay. So what does m minus u look like? Well, that's ax plus cy over bx plus dy minus a over b. So if we want to talk about this, we need to find a common denominator here. Well, the easiest way to do that, ax plus cy times b over bx plus dy times b minus a bx plus dy over b bx plus dy. Easiest way to find a common denominator. Is this the smallest common denominator we could possibly have? I don't know, but it's definitely a common denominator. And that means we can perform the calculation. So that's abx plus bcy minus abx minus a dy. Those two are going to cancel out. Over, I'm just going to leave it as bx plus dy. The reason I'm leaving it, I don't think the denominator is going to matter. This denominator is just going to be positive. So it's all about whether or not this top part is positive. Oh, I probably could have simplified the fraction a little bit more there. So those two cancel out, so we're left with BC minus AD, which we've seen something very similar to that expression before, over B times BY plus DY. Okay. A, B, C, D, X, and Y are all greater than 0. Okay. So bx plus dy is greater than 0. And that top part, so bc minus ADY, is going to be less than or equal to 0 because y is positive. We can divide through by y, and it doesn't change the relationship of less than or equal to. If you divide by a negative number, the sign flips around, and less than or equal to becomes a greater than or equal to. But we know y is positive, so we can divide through by it and say that this relationship holds only if BC minus AD is less than or equal to 0. Or another way to say that is BC is less than or equal to AD. So we don't want that relationship to hold. So is now a good time to focus on V minus M being greater than 0, or should we finish this one off? So our fraction m minus u is going to be less than or equal to 0 only if its numerator is less than or equal to 0, because its denominator is always positive. And this numerator is only going to be less than or equal to 0 if BC is less than or equal to D. BC less than or equal to AD. Okay. Now proof by contradiction worked in D part, so how about we try it again? So how about suppose BC less than or equal to AD? Well, I can divide both sides by BD and not change the sign. BC over BD, well, that's just B. And AD over BD, well, that's just BD, or sorry, AD over BD is just A over B, and that's U. So proof by contradiction is very powerful. You assume the opposite, you assume something is true, and then you show it leads to something that contradicts something you previously knew. We previously knew that U is less than B. We were given that in the problem. And if at any time BC is less than or equal to AD, that would mean that U is greater than or equal to B, and that can't happen. That's a contradiction. So that tells us that our assumption, BC less than or equal to AD, is false. And that tells us that m minus u is never less than or equal to 0. And that tells us that m minus u just must be greater than 0. And that's something we wanted. So we worked out the case where u is less than m. Now we want to show that m is less than u. So v minus m, well, that's just going to be c over d minus ax plus cy over bx plus dy. Okay. Well, once again, common denominator comes to the rescue. I know it seems big and bulky and it's got a lot of the letters in it, but still just a common denominator calculation. Minus dAx plus cy over d bx plus dy. So now we can take that difference. We're going to have a c dy cancel out in both of them. Let's see. It was bcx plus c dy minus adx and then minus c dy all over d bx plus dy. So these two cancel out, and we're left with bc minus adx over d times bx plus dy. So if we multiply through by d times bx plus dy, we know that's going to be a positive integer, so our sign won't change. X is a positive integer, so dividing by it doesn't change around this sign. So we know that v minus m is less than or equal to 0. That is, m would be greater than or equal to v, which is the opposite of what we want it to be true, if and only if bc is less than ad. But didn't we just work that out? If bc is less than or equal to ad, we already showed that that can never happen. So, putting together both facts that we proved, we showed that u was less than m and that m was less than v. We put them together, u less than m less than v, and m was any arbitrary median of u and v. And that's exactly what we were asked to prove. So that's a nice little fraction manipulation question. I rather like that. I think it's quite nice. Good question number 2 for the senior paper. So we have just one more question to go, and we'll take a look at that in the very next video. Thank you so much for joining me, and I hope to see you next time as we finish off the 2011 paper.